Scientists first discovered Arthropleura fossils in 1854 in Great Britain. Some adult specimens reached 8.5 feet, roughly 2.6 meters in length. But from that day forward, for 170 years, not a single head fossil was ever recovered. And without a head, no one could determine what the species ate, whether it was a predator or a herbivore, or even exactly which group it belonged to. For hundreds of years, the body fossils in researchers' hands consisted of nothing more than scattered shell fragments. The vast majority of specimens found were made up of shed leg and shell pieces from adults. Nearly complete examples belonged only to a small number of juvenile individuals. Researchers analyzed fossils belonging to two juvenile individuals discovered in France in the 1970s, working toward finding the first complete head, and published their findings in the journal Science Advances. When the head was finally revealed in detail from these fossils, scientists were able to solve a 170-year-old mystery at last. But it didn't stop there. The details hidden inside the head showed the species in an entirely different light. Researchers discovered that Arthropleura had club-shaped eyes, mounted on stalks. This is an exceptionally rare feature, one not seen among millipedes and centipedes. The research team believes these eyes were probably compound in structure based on the animal's relatives, but this cannot be confirmed with certainty. One researcher couldn't help but ask the question. Today, stalked eyes are a characteristic feature of aquatic arthropods, like crabs and shrimps. Could this mean that Arthropleura may have led an amphibious life? The answer remains unknown. But the question seriously challenges the picture that had been drawn for decades: a giant millipede living in dry forests. The eyes aren't just sensory organs, they may be a clue. That tells us far more than we currently know about the environment of that era. The new head fossils revealed that Arthropleura carried features belonging to both millipedes and centipedes. This creature, classified for decades as simply a giant millipede, actually sits in a position entirely its own, right between these two groups, unlike either. This finding reshapes not only our understanding of Arthropleura itself, but also everything we thought we knew about the common ancestor of these two groups. Researchers now regard this species as a living snapshot of an era, before millipedes and centipedes had fully diverged from one another. Arthropleura's exoskeleton was made up of approximately 30 jointed segments. For every 6 body segments, there were 8 pairs of legs, giving it somewhere between 32 and 64 legs in total. This number and structure contains features that make it more centipede than any modern millipede, and more millipede than any modern centipede, like a photograph taken at the exact moment in evolutionary history, just before the road split in two. Because of its enormous size, it was initially assumed to be a predator, partly due to its scale, and partly because the head fossil remained undiscovered for so long. For decades, scientists were left to speculate based on body structure alone. The most definitive evidence came from microcomputed tomography analysis of juvenile head fossils found in France. There were no venom fangs and no legs specialized for catching prey. Its legs were built for slow movement, not speed, which aligned it closely with the detritus-eating millipedes alive today, the trace fossils known as ichnofossils. The enormous trackways called Diplochnites quithensis, some stretching more than 50 centimeters across, support this interpretation. The morphology of these tracks indicates the animal moved with a slow, lumbering gait, rather than the rapid locomotion associated with active predation. So what we spent 170 years believing was the largest predatory bug in history was, in reality, a colossal debris eater. It carried its massive armor and its weight not to hunt, but simply to wander the forest floor and consume rotting leaves and decaying wood. In 2018, on the beach at Howick Bay in northern England, a block of sandstone fell from a cliff and cracked cleanly in two. Inside were the remains of Arthropleura. Dr. Neil Davies of the University of Cambridge described the find as a complete fluke, noting that a former PhD student happened to spot the fossil while walking along the shore. This specimen became only the third nearly complete Arthropleura fossil ever found. It was also the oldest and the largest. The preserved segment measured approximately 75 centimeters in length, while the original animal is estimated to have been around 2.7 meters long and weighed around 50 kilograms. The fossil was found not in a swamp environment, but in an ancient river channel within an open wooded delta. This shook the long-held assumption that Arthropleura lived exclusively in coal swamps and strengthened the hypothesis that it preferred open woodland habitats. Similar trackways, some reaching 50 centimeters in width, have been found preserved in sedimentary rocks across Canada, France, Scotland, and the United States. Wider than a kitchen table, left behind by a creature walking along a riverbank 300 million years ago. Every documentary, every piece of content on this topic says the same thing. During the Carboniferous period, atmospheric oxygen levels reached 35%. And this is what allowed insects and arthropods to grow to enormous sizes. It sounds logical. But recent findings are seriously calling this story into question. Based on the new Arthropleura remains found at Howick Bay, the species is now thought to have reached giant proportions before atmospheric oxygen peaked. This has led researchers to conclude that a more likely driver of gigantism in Arthropleura was simply the absence of serious competition. New studies suggest that oxygen may not have been the only factor behind ancient insect gigantism. The real answer may involve climate, predators, evolution, and ecosystem dynamics, all working together. One major contributing factor may have been the absence of birds and bats. During the Carboniferous, giant arthropods faced very little competition or predation, in the air and on the ground alike. In short, the oxygen story isn't entirely wrong, but it was probably never a sufficient explanation on its own. The genus Arthropleura persisted for approximately 56 million years, and for the vast majority of that time, it remained the largest animal in its environment. To put that in perspective, all of human history spans roughly 300,000 years. The dinosaurs ruled for approximately 165 million years. Arthropleura was the largest land creature on this planet for a span of time, thousands of times longer than the entire arc of modern civilization as we know it. Arthropleura was able to grow far larger than any modern arthropod, partly because of the higher oxygen pressure in the atmosphere of that era, and partly because large terrestrial vertebrate predators simply did not exist. Today, you could step on a millipede without a second thought. But 300 million years ago, what stood before you on that forest floor was the size of a car, and there was nothing alive capable of hunting it. The Carboniferous rainforest collapse is frequently cited as an extinction factor for large Carboniferous arthropods, such as Arthropleura and the giant dragonfly-like Meganeura. The common theory holds that high oxygen levels led to larger arthropods, and that these organisms depended on forests to survive. According to this theory, the rainforest collapse reduced oxygen concentrations and destroyed their habitat, driving them to extinction. However, later research shows that Arthropleura more likely lived a forest-independent life, and fossil records of large specimens continue to appear after the rainforest collapse. This means that the collapse and the drop in oxygen levels were likely less involved in their extinction than previously assumed. Scientists suggest these coal forests may have contributed to their own destruction. Functioning as extraordinarily efficient carbon dioxide sinks, they buried atmospheric carbon into the soil. gradually cooling the Earth. As the climate changed, this hot and humid environment gave way to the cooler, drier climate of the Permian period. So what wiped out Arthropleura was not an asteroid or a sudden catastrophe. Its own habitat slowly dismantled itself. And the process bears an unsettling resemblance to the climate dynamics we observe in the world today. If this video made you see the ancient world a little differently, then it did exactly what it was meant to do. Leave a comment telling me which fact surprised you the most. And if you want to keep exploring the hidden history of the insect world, from the creatures that came before the dinosaurs to the ones living beneath your feet right now, subscribe.